First step is subtracting each value by the mean. The mean number of classes was 4, and that's a column of data that we're working with right now. So we'll subtract each answer for number of classes by 4. We're subtracting each data value by the mean of the entire set of data. Well, I mean, we're subtracting each data value by the mean of the entire column of data. The answers that we get are called deviations. We'll just put DEV for deviations. Three minus 4 is -1. 4 minus 4 is 0. 5 minus 4 is 1. And 4 minus 4 is 0. These are called deviations because they're showing how far each data value deviates from the mean. We can also ignore negative signs and make a column of absolute deviations. This column is just going to show the absolute value of each deviation. The absolute value of -1 is 1. The absolute value of 0 is 0. And the absolute value of 1 is 1. We're just ignoring all of the negative signs. These numbers are just showing the absolute distance from each of the data values to the mean of 4. If we calculate the mean of these absolute deviations, our answer will be called the mean absolute deviation. If we add these up and divide by 5, we get 2 over 5. 2 divided by 5 is 0.4. So the mean absolute deviation of this column of data is 0.4. We can put that under here. I'm just going to use some abbreviations. The mean absolute deviation. The reason why we found the absolute values is because we didn't want to deal with these negative signs. What would happen if we just added up the deviation column? If we added up the deviations, we would get 0 because the negative and the positive cancel each other out. -1 plus 1 is 0, and then if you add all the other zeros, you get 0. Actually, these deviations will always add up to 0 for any column of data, and when they add up to 0, you can't do any more steps, because if you divide 0 by something, you just get 0. So we had to create these absolute deviations to make all of the deviations positive. There's actually another way to make the deviations positive besides taking absolute values. You can square the deviations and make a column of squared deviations. Let's square each of these deviations. -1 times -1 is 1, because a negative times a negative is a positive. 0 times 0 is 0. 1 times 1 is 1. 0 times 0 is 0. And 0 times 0 is 0. It's not always going to come out this nicely. The square deviations usually won't be all the same as the absolute deviations. What if we calculated the average of the squared deviations? What would we get? What if we calculate the mean of the squared deviations? One plus 0 plus 1 plus 0 plus 0 equals 2. 2 divided by 5 is 0.4 again. These usually won't come out exactly the same, but they did in this case. So the mean of the square deviations is 0.4. What would happen if we took the square root of the average of the squared deviations? What would we get? We get 0.63. So you find the average of the squared deviations. You get 0.4. And if you go one step further and take the square root of the mean of the squared deviations, you get 0.63. Both of these values actually have a name. The mean of the squared deviations is called a variance, and the square root of the variance is called a standard deviation. If you calculate the mean of the squared deviations, your answer is called a variance. And if you take the square root of the variance, you get the standard deviation over here. The standard deviation is, well, the variance is the mean of the squared deviations, and the standard deviation is the square root of the mean of the squared deviations. And these are actually two other measures of dispersion besides the mean absolute deviation. And we can see that the variance, meaning the mean of the squared deviations, actually came out to 0.4, just like how the mean absolute deviation came out to 0.4. Once again, the mean of the absolute deviations is the mean absolute deviation, the mean of the squared deviations is the variance, and the square root of the mean of the squared deviations is called the standard deviation. The standard deviation usually comes out to a number that's close to the mean absolute deviation. So these two numbers usually come out to similar numbers. And the standard deviation is actually used more often with actual data collection. Usually the variance won't be the same as the mean absolute deviation. It'll usually be bigger than the mean absolute deviation because the squaring will make the numbers larger. Right now I'm just using some abbreviations for standard deviation. Now, they've actually invented an adjustment to the formula for variance and standard deviation, and that adjustment is used when the data comes from a sample and not from an entire population. What if, instead of collecting data from the entire population, we just recruited a sample of the population, maybe 3 out of the 4 people, and then we wanted to calculate the standard deviation with the sample and not the entire population? Since our data is from a sample, you would have to use the adjustment that I'm talking about. So now we need to find the mean of our sample. We need to find the mean of the number of classes and of the 3 people in the sample. It actually still comes out to 4, I think. Usually it won't come out the same, because usually when you take a sample out of the population, the mean of the sample won't be the same as the mean of the entire population. But in this case, it happens to be the same. Let's subtract each of our data values in the sample by the mean. It's important to realize that what we're subtracting by is the mean of the sample, not the mean of all 5 numbers. We get our deviations of -1, 0, and 1. Now what we want to do is get the squared deviations. We actually don't have to get the absolute deviations first if all we want is the squared deviations. So let's go straight to the squared deviations. -1 times -1 is 1. 0 times 0 is 0. And 1 times 1, or meaning 1 squared, is 1. Now, what if we want the variance of the sample? These are our squared deviations. What we actually do is we calculate an adjusted average. Instead of dividing by the number of numbers, we divide by 1 less than the number of numbers when the data comes from a sample. So we actually add up these 3 numbers and divide the total by 2 instead of 3, because 3 minus 1 is 2. If you want to see the adjustment, we could even write 3 minus 1 under here. We get 2 on top, we get 2 on the bottom, because 3 minus 1 is 2, and it comes out to 1. So the variance of our sample came out to 1. What this variance that we calculated is actually called is a sample variance. That's called a sample variance because the data came from a sample and we use the adjustment that we have to use when the data comes from the sample. The value that we calculated when we calculated the variance of the entire population right here would be called a population variance. The reason it's called a population variance is because the data that it was calculated with was an entire population and the adjustment wasn't used. We divided by 5. We didn't drop this number down by 1. So the answer is called a population variance. What if we wanted to take our sample variance of 1, which we found right here with the adjusted formula, and find its square root? What would we get? The square root of 1 is 1. We've done the same step that we did with our population variance up here. The answer here, right here, is actually called a sample standard deviation. And the answer up here would be called a population standard deviation. So when you take data from an entire population and you calculate the variance with the unadjusted formula, you get a population variance. And then when you take the square root of the population variance, you get a population standard deviation. If you have data from a sample and you calculate the variance with the data from the sample using the adjusted formula, you get a sample variance. And if the sample variance is right here, actually. And if you take the square root of the sample variance, you get a sample standard deviation. And all of these values that we've talked about are meant to be measuring the spread of the data. The mean absolute deviation is one approach to measuring the spread of the data. The variance and standard deviation are another approach to measuring the spread of the data. So you might be wondering, why did we use this adjustment when the data came from a sample? The reason is because the purpose of calculating the variance or standard deviation of a sample is to estimate what the variance and standard deviation would equal if you had been able to use data from the entire population. In other words, the sample variance and sample standard deviation are meant to estimate what the population variance and population standard deviation equal. When you take a sample from a population and record the data, the variance and standard deviation of your sample tend to underestimate the variance and standard deviation of the entire population. The reason is because samples tend to have less spread in them than the entire population has. When you collect data from a sample, you tend not to capture all of the spread that's found in the entire population. So overall, we do this adjusted formula for sample variance and sample standard deviation to try to compensate or make up for the fact that they tend to underestimate what the population variance and population standard deviation equal. When you divide by 1 less, you divide by a smaller number, because 2 is smaller than 3, and by dividing by a smaller number, you're increasing the variance and you're increasing the standard deviation. And the purpose of doing that is to bring these values up closer to what the population variance and population standard deviation equal. And the sample values, the sample variance and sample standard deviation don't always underestimate the population variance and standard deviation, but there's a tendency for samples to often underestimate the population variance and population standard deviation, which is why this adjustment is used to increase the sample values. One other thing I wanted to talk about is the idea of the shape of the data. We talked about the mean and we talked about the spread of the data, but I also wanted to talk about the shape of the data. Before I do that, let's look at these values down here. Well, actually, I didn't calculate these values with all 3 columns of data, but if I had calculated them with all 3 columns, you would have seen that the mean absolute deviation would increase and be a higher number when the data has more spread. So the mean absolute deviation would be lowest here, it would be higher here, and it would be highest here. The variance and standard deviation would be the same way. The variance would be smallest here when the data has the lowest spread, and it would get higher for columns of data with more spread. The standard deviation would do the same thing. It would be the smallest here when the data has the least spread. It would be higher when the data has more spread, and the highest when the data has the most spread. So now let's talk about this idea of the shape of the data. I just have to free up some space. We could create something called a histogram. Which is a certain type of graph. We put the possible values down here. The values that were in our data set. We have tick marks on the y-axis. And we count the number of threes in our column of data right here. We have 1, 3, so the bar goes up to 1. We have 3 4s, so this bar goes up to 3. 1, 2, 3. And about how many 5s? We have 1 5, so this bar goes up to 1. We could make a histogram for these other columns also. If there's a number somewhere along the way that doesn't ever appear, you still put it down here on the number line. You don't want to skip over numbers. For example, you don't want to go from 0 up to 2. That distorts the shape of the graph. We'll include 4 also, even though 4 doesn't appear. How many zeros do we have? We have 2 zeros. How many 1s? We don't have any. We have 1, 2. We have 1, 3, and we have 1, 5. These bars are supposed to be touching in this type of graph. And we won't do it for age, but we could make a third histogram for the age column. And you can see that this is showing a shape. You can see the shape by drawing a curve around the bars. By drawing a curve that outlines the bars. You can see that in this shape right here, the data is, the shape is going up and then it's going back down, which means that most people have values in the middle and fewer people have lower and higher values. We can see right here that we have a shape. Most people are at the low end. We have the largest bar at the low end because 2 people have zeros, and we have fewer people at each of these higher numbers. So the shape peaks at the left end and goes down like this. And they have names for the different types of shapes that can appear in the histogram. Let's look at some examples of different types of shapes. This isn't opening up very quickly. I think it's going to open right now. I'm going to try to roughly draw the shape of a bell-shaped curve in a histogram. This actually isn't perfect, but it's close enough. If you have a shape like this that follows a bell, it looks like a bell, then it's called a bell-shaped curve, or the more technical word is called a normal distribution. You would say that this data is following a normal distribution. Because it peaks in the middle and it has this bell shape. Don't worry about why the word normal is used. Sometimes in statistics they take words that have meaning in everyday life and they give them technical meanings. If the data doesn't peak, if the histogram doesn't peak in the middle and it peaks at the left or right end, it's called a skewed distribution. Here's an example. If it peaks at the left end and then trails off to the right, it's called either a positive skewness or it's called a histogram or a data set that's skewed to the right. Let's talk about where those names come from. Or wait, let's talk about how you can remember those names. I said this is either called a positive skewness or it's skewed to the right. Those are two different names for this shape that we see here. When you look at the way it's sloping down, you can see it's sloping toward the positive end or toward more positive numbers. Or you could say it's sloping down toward the right. That's one way to remember that it's either a positive skewness or skewed to the right. If it peaks at the right end and it trails off to the left, then it's called a negative skewness or it's skewed to the left. Those are two different names for it. You can remember it this way. It's trailing toward the negative direction or it's trailing to the left. I could also draw a curve around this to show the shape. So we have a normal distribution in the middle. Over here we have a distribution that's positively skewed or skewed to the right. Over here we have a histogram that's negatively skewed or skewed to the left. You have to remember that the name skewed to the right doesn't have to do with the side that it's peaking on. It has to do with the side that it's trailing off toward. If it peaks at the left end and trails to the right, it's actually skewed to the right. If it peaks at the right end and trails off to the left, it's actually skewed to the left. If it's skewed to the right or positively skewed, it means that most people have values at the low end and fewer people have higher values. If a test is difficult, most students will get lower grades and fewer students will get the higher grades up here. So the exam scores on difficult tests are skewed to the right. If a test is easy, most people will get the higher exam scores up here and fewer people will get the worse exam scores down here. So if a test is easy, the grades will be skewed to the left because you'll get a lot of scores piling up at the high end. A lot of people will get A's and B's, and fewer people will get C's and D's down here. There's a couple of other shapes we'll talk about. There's one type of shape that peaks higher than a normal distribution, and one type of shape that peaks lower than a normal distribution. Let's draw the curve that outlines a normal distribution right here. I'm just going to try to roughly draw it. If the bars in the center peak higher than the normal distribution, then it's actually called a positive kurtosis. If you have a shape that peaks higher than the normal distribution does, and it also has a more abrupt peak, like this, it's called a positive kurtosis. For a positive kurtosis, you can imagine that the data in the shoulder areas right here are being pushed toward the center, and it's peaking higher, and it's also having longer tails right here. This is a positive kurtosis. If a lot of people get C's on an exam, and few people get any other grades besides C's, you have a positive kurtosis. Positive kurtosis is more peaked than a normal distribution. You can also have a shape that's more flattened out than a normal distribution. Keeps doing that. Let's draw the normal curve again, the normal distribution curve. If you have a flattened out shape like this, that peaks lower than a normal curve, it's called a negative kurtosis. So if if the students in a class are all getting fairly similar grades, meaning no grade is appearing much more often than any other grade, then the exam scores have a negative kurtosis. So you can see that we have a normal distribution. We also have shapes that are shifted to the left and shifted to the right, like this. This one is actually called skewed to the right because of this arrow. This one is called skewed to the left because of this arrow. You can also have a shape that's shifted lower than a normal curve or shifted up higher. That's when you have a certain type of kurtosis. Over here you have a negative kurtosis. Over here you have a positive kurtosis.